Hello and welcome to the second part of the lecture Machine Learning for Robotics and Computer Vision. In this lecture we will cover regression, and to just give you a little bit of recap of what happened in the last lecture. So there we had a high-level overview of learning models, and we discussed the main ingredients of this learning models, so of the machine learning algorithms. So the data part, the model, and the learning. So we gave only a very rough overview of what happens there, and in this lecture we will more focus on specific models for regression and how to learn these regression models. In the introduction lecture we also had a very simple example of a machine learning algorithm that does classification, and in this case this was the k-nearest neighbor classifier. But in this lecture we will now focus more on the regression part. So as you might remember from the first lecture, regression deals with finding a function f of x of a feature vector x that explains our targets y, which are now continuous values. And the feature vectors are given by d-dimensional vectors here. And as can be seen here, so we have maybe some training examples, and then we want to find a function that explains these training examples, and then with this functional representation we then can also derive the values for unseen parts of the data. The assumption that we are now doing is that our targets are noisy observations. So that means that the function that we are looking for, which comes from the x of n, is corrupted by some noise value. And in this case we are assuming here normal distributed noise, which has a standard deviation of 0 and is centered at 0, so it has a mean of 0. So and we assume for now that we are knowing the sigma square in advance. And we are focusing here now in this lecture mainly on linear regression. So here we are having the assumption that under this assumption that we have normally distributed noise, we can now write our model, our probabilistic model that which gives us the probability for a certain target value given our feature vectors x and our parameters theta as a normal distribution, which has the mean f of x and the standard deviation sigma square. In linear regression we are assuming that the parameters thetas appear linearly in the model. So that means that the f of x is a linear combination of the feature vector x and the parameter vector theta. And we add here theta 0 to have also functions that are not only passing through the origin. So the theta 0 is called intercept or bias, and as I said, with this theta 0 we have the ability that we also have functions that are not only going through the origin. To remind you a little bit of what happened in the first lecture, so we had there the so-called training data, and then this was the set of paired examples. So that means we have a feature vector x and a corresponding target value y1, and these are pairs, and we have n of these training examples, and the feature vectors are given by a d-dimensional vector. And here we have x1 to xd. And the target value is of course continuous in the regression task. To simplify the notation forthcoming now a little bit, we are adding just the x0 and that is to 1. And this has the advantage that we then can write the functional representation in a shorter form. So that means that we can replace, when we put this 1 in front of the vector, we can then replace this x transpose theta plus theta 0 with x transpose theta. So this you have to keep in mind, that we always have this bias in front of the vector. And to make the notation a little bit shorter, we will also use the shorthand here for the concatenation of multiple variables, where we just say, okay, the variables x1 to xn are given by this x1 colon n, and the same we are doing for the y. And this makes the notation a little bit shorter. So we are now having here a probabilistic view of the problem, and we are also taking this probabilistic view for the theta value. And we are taking here we are treating the theta as a random variable, and that means we are interested in the end in the probability over all thetas given our training data. And this can then via Bayes represent rewritten as follows, so that we have the p of y given x1 to n and p of theta, and divided by p of y given x. And for now we can drop this denominator here because this is independent of theta, and then we are talking here always about the posterior over the theta, and then the likelihood and the prior. So this also are terms that you usually will see in literature when you see machine learning algorithms. When we are talking about the denominator, we are also saying that this is the marginal likelihood or evidence. There are now, for estimating a theta using this probabilistic assumptions, different ways to do this. And we will discuss in the upcoming part of the lecture now these different ways. And the three main paradigms to estimate the parameters are the maximum likelihood estimation, the maximum a posteriori estimation, and the Bayesian estimation. So in the maximum likelihood estimation and in the maximum a posteriori estimation, we are just interested in a specific theta. So we want to find the theta that maximizes the likelihood, or the likelihood plus the prior. And in the Bayesian estimation, we want to determine the full posterior over all thetas. So each one has a different advantages and disadvantages, and we will see later what are the benefits of having a certain view on the problem. But let's now start with the maximum likelihood estimation. So as I said, so in the maximum likelihood estimation, we are interested in a specific parameter. And here we make the assumption that we have a uniform prior, so that means we treat all parameter values the same, and this leads to that we can drop the prior here. So that means that the posterior is just proportional to the likelihood in the end. And we want now to find a specific parameter, theta star, which maximizes the likelihood. And this comes then to this problem that we have the argmax over all possible thetas, given the likelihood over all targets, given all all training feature vectors, given the theta. And this is what we want to maximize in the end. And when we then replace, or when we just use, maybe remember from the first lecture, that we assume that our examples are generated independently. And with this independence assumption, we can then write the joint probability over all targets given all training examples as just as a product. And this, makes the derivation a little bit easier in the end. When we now have this optimization problem, we can use certain tricks to make it a little bit easier, also for the derivation in the end. And the first trick that we are using is here that we are using the logarithmic log transform. And because the logarithm is a monotonically increasing function, and that means when we apply the logarithm to a function, then the optimum of f will be also the optimum of the log of the function f. And by using this logarithmic transform, we can then write we can add the logarithm in front of the product here, and usually we are not maximizing, we are just wanting to minimize the objective function here, and with this view we just have to add a minus in front of the problem that we had before. So when we put a minus in front of it, then the maximum here turns into a minimum. So this is the only thing that we did here. So we had the minimum, the minus and the logarithm of this, and then when you remember this from calculus, when you have a logarithm of a product, then you can turn this product into a sum. And this is usually then called the negative log likelihood. So, and one specific advantage of this logarithmic transform is that we turn the product of small numbers into a sum of small numbers. And by using this, this gets a little bit more numerically stable, because we are not building products of numbers between 0 and 1, but we are now doing a summation over the values. And this has the advantage, and also because using the logarithm, as you will see shortly, has also some other advantages that will simplify the derivation a bit. When we now insert all the terms for the linear regression, so you might remember that we have the definition that we have P of y given x of n is given by a normal distribution with the mean f of x of n and sigma square. And then we just put in the definition of a normal distribution, then we get the following. And when we then further plug in the definition of f of x, which we now assumed as a linear combination of the feature vectors and the parameter vector, then we can put in this for the mean of the normal distribution, and then we get this term. And as I said, when we now use the logarithm of the probability of this likelihood, then we can use the logarithms to simplify these terms. So the logarithms turn this function basically into a function where we have some constants, and we can replace the exponential with this exponential goes away, and then we have this is the remaining part of this whole normal distribution here. And when we then plug this into our negative log likelihood, then we get this whole term here. So we have then the sum over the square of the target minus the estimated value, and we have some normalization term in front of this. To make the notation a little bit easier also for the upcoming derivations, we are now defining here two terms. So the first term is the so-called design matrix, which is given just by turning all the examples from the training set into a matrix where each feature vector is now a row of this X matrix. And the same we are doing for the targets. So we are building here a column vector where we have all the targets organized like this. When we use these definitions, we can then turn this sum into a product of two matrices, then we get a little bit shorter notation. And you might remember from analysis, so because we have here now a quadratic function in the terms that we are interested in, so this theta, and when we have a quadratic function, we can just find the minimum by finding the point where the gradient is 0, and by using this we can then just determine the minimum in a closed form. So we are first determining the gradient of the log likelihood and set this to 0. So and for the gradient derivation we are doing now the following. So we are interested in the gradient of the log likelihood in respect to theta. So we are putting the derivation in the derivative in front, and then we have here a constant term, so we can just put this out. And the first thing that we do, we are just writing out these terms here. So we have then y transpose times y, and then the rest of the binomial function that we can use here. Since the y is now independent of the theta, we can just drop this. And then we are left with those two terms here. And with matrix calculus, it's the same as with the, or with the vector matrix calculus, it's the same as with the normal calculus. So we are just having here a linear term that's depending on theta, and here a quadratic term. So when you look up in the books, then you find that here this theta is just dropped, and here the theta gets also dropped. So we are just left with these terms here. And the whole product then gives in the end a row vector. And then, as I said, to find the minimum, we are essentially setting the gradient to 0. So, and with this then we're getting the optimal point that we want to have in the end. So, when we are, this was the last equation from the slide before, when we set this to 0, we can then simplify this terms a bit. So we are now solving such that we have theta then on one side of the equations and then the rest on the other side. The first thing that we do is basically multiplying this part with the constants so that they just vanish because this is 0 on the other side. Then we are putting this term on the other side, and then we have the 0 here that can also go away, and then we are just using normal matrix calculus and multiply both parts by the inverse of this x transpose x. And then the last thing that we do is basically turning this theta transpose into a column vector again, because you remember from before, this is a row vector, so by turning this then back into a column vector, we have to use here this small hint that the A times B transpose is then B transpose A transpose, and when you do the whole derivation, then you will find out that theta is in the end x transpose x, and the inverse of this times x transpose times y. And this you will find also in the literature, that is often called the normal equations. So that's the thing. So, and equipped with this, we can then determine this theta in this maximum likelihood estimation, and we can then fit to our data sets. So that means we have now here this examples given for a training set, and then we can determine the theta that maximizes the likelihood in the end, and then with these terms we are getting then this line fit. So we are now equipped basically with the knowledge how to fit lines to points, but the more interesting functions are maybe nonlinear functions like this. And when we have now such data set like here, so with training examples x, with this target values y, then when we just fit the line here, then this is not a good explanation of the data set. So next thing is, how can we use maybe the derivations that we already did, such that we also can fit nonlinear functions. And as it turns out, this is quite simple, because we only said that the linear regression is linear in the parameters. So that means we can do whatever we want with the input and then have just a linear dependency with the parameters. And this is exactly what we want to exploit here. So we are just applying some nonlinear transformation on the x, and then we have still the linear dependency here. And now we can use some nonlinear transformations so that transforms our points in a certain way, so that we are getting from the d-dimensional vector in a new space where we have k dimensions in the end, and then we just do the same trick as before. We're just defining our design matrix, but now not using the original x vectors, but this transformed vectors. So that means we apply to our training examples this phi, and then have the transpose here. So the structure of this matrix is exactly the same. But the only thing that changes is that now we have more columns than before, maybe. And by using this, we then can find out that everything stays the same, essentially. So we can basically use this nonlinear transformation on our training examples, and then just have the possibility to also fit nonlinear functions. So in the end, it just turns out that we can just use the normal equations with this specific design matrix where we have the nonlinear function inside. And one specific thing that one can do to also fit nonlinear functions is to use the polynomial transform, where we just replace all x's by the polynomial transformations of them. So that means we turn the x1 of a vector to x1, x squared, x cubic, and so on and so on. And we do this for the whole vector so that we get in the end each entry, the quadratic entry, and so on. So that means also that our parameter vector grows, of course, because we then have also parameters that take care of the quadratic part or the cubic part and so on. And with this, then we can then fit also nonlinear functions at the end. And when you now use the degree 1, so we just have k equals to 1, then we just have the original feature vector in the end. And this results then in such fits. For instance, for degree 3, we can then fit the data that we saw before quite reasonably. But the question is now, maybe we can do better by using a larger degree. And when we now apply this, so we have here the degree 3 function, we can then maybe just say, okay, we now take for the polynomial transform k equals to 5, then we can maybe get something like this. And here you can see that we are in this part closer to our data, so that's maybe a good choice here in this case. But maybe we can do even better. And therefore we are increasing the k a little bit more, so we have now degree 8. But as you can see here now with this maximum likelihood estimation, we are getting such weird behavior here in the end. So the points are now maybe fitted optimal, so the functional explanation of the points goes just through all the points, also through these points, but we have these parts in between where we maybe have not very optimal fit. So it's maybe not a good explanation of the functional relation here, because this point maybe is maybe just an outlier, and we don't want to have the function in the end such that it also accounts also for these outliers and maybe in between makes weird things that we don't want to have. So it's the function that we have in the end is not a good explanation of the underlying process, because here we have large jumps which might not occur in reality. And with this implausible shape, we are getting to the point that we have here a really bad overfitting. So the maximum likelihood estimates are prone to overfit especially when you have only a few data available. And then you also produce overconfident predictions, because in the end, when you fit it too much, then the probability that you get an out in the end is too high. And usually the root cause here is that we just have too large parameters, so our theta is getting too large. And this is also happening when we have too high capacity. So we talked in the first lecture about the capacity of the model, which is basically related to the amount of parameters that we have. And when we have a lot of parameters available, then we are able to fit the training data too well. And in this case, we are not maybe generalizing again to unseen data very well. So as the root cause are too large parameters, one easy solution would be to ensure that the parameters don't get too large. So, and this we can do by exploiting that we have this prior available. So with some prior information, we maybe get in the end some better fit, because we can just say that we want to have values from the prior that are small. So this is our prior knowledge that we can put in there. And this leads us to the so-called maximum a posteriori estimation, or MAP. So when you just do the same derivation as before, we are now assuming for the prior, again, a normal distribution, but here we have now the b squared, so that is the assumed shape of the prior distribution. And as you see, because the prior is now going over theta, we have now a multidimensional normal distribution here. And with this, we then can plug this just into our derivation from before. So we just have this additional term with the negative log likelihood here. And inserting the Gaussians then again leads to this, so that we get additionally this term here, which is just the length of the vector, so to say, of theta. And when we then use again the same rewriting with the design metrics, and here I included actually the phi, because we are now, it doesn't matter if we take what transform we now use, so we can also apply this, of course, for nonlinear transformations and so on. And therefore, I'm using here the phi instead of the x. And when we use the same recipe as before, so we have this function, and then we want to set it to 0. We do the derivation again, so that means here we just rearrange the terms a bit so that it gets a little bit easier to do the derivation in the end. So then it turns out that we can put this term on the other side, the constants vanish, and then when we see the theta transpose, when we have here the inverse of this multiplied by this other side, we then get in the end actually a very similar expression as with the maximum likelihood estimate. But when you compare these the two normal equations that we get in the end, then you will see that the one additional term that comes to this is this added identity matrix here. And when you think of it, it can be thought as a penalty term. So, and with this, we are then getting hopefully a better estimate, as I will now also show in an example. So when we now compare the maximum likelihood estimate and the maximum a posteriori estimate, then we can see that when we have a small degree, then the influence of the prior is not so large. But when we go to higher dimensions, then you will already see that there is some difference between the maximum a posteriori estimate and the maximum likelihood estimate. So here in orange is the maximum a posteriori estimate. And with higher degrees, we then get more reasonable functional shapes. And of course, we are now having to deal also with this hyperparameter, which we have to choose, so the beta square or the b square. This is, of course, then a parameter, as we discussed in the beginning, in last lecture, which we can choose basically on a validation set, for instance. And with this, we then get very reasonable results in the end. But when we come back to the probabilistic derivation, then we saw that the posterior is given by the likelihood plus the prior. But for the maximum likelihood estimation and for the maximum a posteriori estimation, we are just getting one specific parameter out. And as we will see in a bit, it turns out to be, it has some advantages if you just get the whole posterior out of this function. And this is then the part that we are dealing now with. So how do we determine the posterior over all parameters? And this is the so-called Bayesian approach. So in as I said, in the maximum likelihood and the maximum a posteriori estimate, we are just getting the most likely parameters. So we are always maximizing something like this. But with the Bayesian approach, we are actually estimating the whole posterior over all parameters. So and when we as I showed in the beginning, so the posterior over the parameters is given by the likelihood plus the prior plus the divided by the marginal likelihood. And as one can derive or one can see from the assumptions is that when we can rewrite the marginal likelihood in terms of the likelihood and the prior, which is just the integral over both. And when we now have basically the posterior over the parameters, so this p of theta given x1n to yn, we can then estimate an unseen point, which we not seen before, by using the posterior predictions. And here we are basically interested in y star given all the training data, and then we integrate all the parameters. And as you can see here, this is then integral over the likelihood of the specific y star given the x star, so our input. And this is weighted by the posterior. So, and this takes into account the uncertainty of all the parameters. So we can have here now a weighted sum over the all possible parameter values, basically. And for each of these parameter values, we get out a probability. And by using this, we can then introduce the uncertainty also in the parameters. When we are now talking about the Bayesian logistic regression, then Bayesian linear regression, sorry, then we can just use the same assumptions that we had before. So we are now keeping here the multivariate normal distribution and not rewrite the likelihood in a product of the individual terms, because that's from the derivation some advantages. And therefore we have here now a multivariate normal distribution where we have the mean of the parameters are given by the phi times theta, so our functional representation. So you remember phi was the design matrix with the transformed feature vectors. And we now have here, this is the special part, we have here now an isotropic covariance. And then we have here the prior, and here we are using, just to make the notation a little bit clearer, we use here for the prior some mean m0 and the covariance sigma or s0 here in this case. So I kept these terms to make it also consistent with the mathematics for machine learning. To derive now the posterior, we can exploit that we have the marginal as a product of the likelihood and the prior. So that means here it's highlighted in blue. So basically the term in the numerator is turning up here in the integral, and therefore when we find something for the numerator, we can just plug in this into the integral and then hopefully get out something sensible in the end. When we now insert just our choices for the likelihood and the prior, then we get the following. So we have now here a product of the normal distribution over y and the normal distribution over theta. So the good thing here is that we can hopefully exploit is that we have here a product of normal distributions. But the problem here that we have is that one normal distribution goes over y, and here this goes over theta. So what we want to have in the end is a product where we have theta also here. So, and when you look around, then there are certain theorems for normal distributions, and there is also the theorem about the change of variables. So when we consider a normal distribution with a mean that is given by a linear function, so that means we have a normal distribution over x, where now the mean is a linear function of another variable, in this case y, so that the mean is given by a times y plus b, then we can change the role of the variables in this normal distributions by using these terms here. So the normal distribution over x is then the normal distribution over y times some normalization constant. And the new covariance is just the product of A transpose times sigma inverse times A. And from this the inverse. Then we have sigma prime. And then we can derive also a new linear transformation here. And this is just sigma prime. So this part here goes there times A transpose times sigma inverse. And so this is the sigma from here. And then the new B prime is then given by minus A prime. So this term here times B. So, and yeah, the normalization constants just for completeness is given by the determinant of A. And when we use this theorem and use all the definitions from there, we can then rewrite our normal distributions that goes over y in terms of theta. And here I replaced this, I just kept the normalization constants like this. So because in the end it will hopefully vanish. And I just put here the terms from before, and yeah, to make it a little bit easier to understand, so I highlight here that's the A. So in our case, this, the phi matrix is our linear transformation matrix. We have no B, therefore B is dropped here, and we have the sigma, and the sigma is in our case this sigma square times the identity matrix. And with this, it turns out that we have here now the phi's turning up, and we can exploit basically that here we have the identity matrix, so the thing that goes in between. So the inverse of the identity matrix is of course the identity again, and when we apply basically the inverse to the sigma square, then it's just 1 divided by sigma square. So then sigma times sigma to the power of minus 2. And yeah, the same we can do then also for the sigmas and so on. So, and yeah, this term just goes here, so we can just copy this, and then we have again here exploited that we have the identity matrix, and with this then we can turn this into the following terms here. And next step in the derivation is that we want to compute the product of two normal distributions. So we have now normal distributions in terms of theta times a normal distribution in terms of theta, that's the prior. And when you then again look in your math books, then you find that the product of Gaussians is also given. And the product of Gaussian, that's maybe an advantage, turns out to be that it's also a Gaussian again, so an unnormalized Gaussian. So the unnormalization comes from this because this is an additional term that comes in front of this. And we have here now two normal distributions, one with A as mean and capital A as covariance, and the other is B and capital B as covariance. And then when you, this results in another Gaussian or normal distributions where we have now C as mean and C as covariance. And then I wrote it again, or the authors of the mathematics for machine learning wrote it again, like that you have here the C is given by A, the inverse of A plus B, plus the inverse of B, and from this the inverse again. And then you have the mean, or the new mean of the new normal distribution is then given by the product of this new covariance times, basically a weighted mean of the, or a weighted average of the means from the original distributions. And the normalization constant here, it's now written as some kind of normal distribution, but it's not really a normal distribution, but to make the notation a little bit shorter. So because here we just have no random variables involved, but really scalars or vectors in this case. But from the intuition, you can see that the the mean is somehow an average between the two means that you had before, so A and B, transformed with the covariances, and that the new covariance is also some addition of the both terms. Using this definition, we can then plug in these terms into the derivation again. So then we can use the product, we can simplify these terms more. So we have now here the two normal distributions, and we can then just use the definition from before. So we have here the terms that came from the A and the terms that came from the B. So this comes from this. So yeah, so this first term came from the change in the variables, and then we use this together with the product formula, and I colored here the different terms to make it a little bit easier to understand. So we have the A covariance is given by this term, and the B covariance is given by the S0, and then we have the one mean is given by this term here, and the other mean is given by the M0. And then when we use just the theorem from before, we can then replace the new found covariances by these terms and the new mean by this term. And then when you plug this all into this formulas here, then you will see that these both terms cancel out. And with this, we are then getting to this, this short term here in the end. And now we have basically derived the numerator. So the numerator is then given by by this normal distribution and these normalization terms, which are somehow maybe not so nice to have in the end. But as it turns out, we can now plug in the numerator just in the denominator. So okay, sorry, some technical issues. So the denominator is then given by this integral over this both terms. So we had here the likelihood and the prior information. So we then can plug this in here, and as we can see, these are just constants, so we can put it in front of the integral, and then we have the integral over a normal distribution. And yeah, because it's a valid probability density, so when we sum over all values of this normal distribution, this is of course then 1, and then we are just left in the denominator with the constants in the end. And when we now put everything together, then we get in the end the following nice form of the posterior, which is just then Gaussian with this mean and with this covariance. And one nice property is now that the posterior is in the end of the same shape or form as the prior. And this is maybe not an accident, because the normal distribution is self-conjugate to itself. So that means a prior is conjugate to a likelihood if the posterior has the same form or type as the prior. And as I said already, so the Gaussian with a known sigma is basically a self-conjugate to itself. So that means that when we combine Gaussian distributed likelihood with a Gaussian distributed prior, then the posterior will turn out to be also Gaussian distributed. And the conjugacy of the prior and the likelihood leads in the end also for other distributions for closed form solutions of the posterior in the end. And the thing that you can exploit or that you can see here is basically that the posterior is just the prior with updated parameters. So we change the mean and covariance of the prior, and then get a an updated prior and posterior estimate. And then we can plug in all these derivations now also for the posterior predictions. So remember that for unseen data, we basically have now to integrate over all possible parameter values and weight them via the posterior and the likelihood. And when you plug in everything, then you see also that here you have an integral over two normal distributions. And you can now do the whole thing again, so which I will not do now here, to change the variables, build the product, and so on and so on. And when you do the whole derivation, then you can see that it gives out you also a normal distribution in the end. So that means for an unseen data, we get then the normal distribution with this mean and with this standard derivation. And when you see this, then you can see that this mean of the prediction basically corresponds to the maximum a posteriori estimation. So that means that's somehow what we wanted to have in the end. So the maximum of the posterior is basically the mean of this normal distribution. So, and when you then apply this whole thing to our example or to one example of for regression, then you can see the following. So we have here now the maximum likelihood estimate in blue again, the maximum a posteriori estimate in orange, and we or the authors of the machine learning and of the mathematics for machine learning book visualized here also the confidences in the values, so the confidence intervals over the predictions, which you get out when you do the Bayesian estimation. And when you then take, here on the right side, it's always shown when you then take with your posterior, you can then sample different theta values. And with a different theta, you then get a different shape of the functions. And here on the right sides are just different functions that you can get with different theta values out. They are sampled. And as you can see, they are lying in the confidence intervals because, that's what the confidence tells you. So, and this is now here within degree 3 polynomial. When we increase it to 5, then we get this shape. As you can see, the maximum likelihood estimate and the maximum a posteriori estimate are a little bit different. But what you also can see is that the confidence intervals grow. Because in between, because we have now more freedom for the function, we can also now have different explanations that are equally good from the fitting to the individual points maybe, but in between the function can vary much more, and this comes from the higher degree here. And this is then for degree 5, and then when we further increase and give the functional representation even more freedom, then you can see that here the maximum likelihood estimate, as we saw, is heavily overfitting here in this case. The maximum a posteriori estimate is doing a better job in between, so we are not getting these excessive values. But what you also can see, what gives you now with the Bayesian approach, is that you can also see the confidence intervals are growing much more. So that tells you, for instance, in this region, that you are very uncertain what happens there in between, because you have you can have very different shapes in this area of the estimated function. And this is maybe a nice property of the Bayesian linear regression in the end, that you can also get some information where you might have to gather additional data to get better estimates about the functional shape there. So from this you could see that by maybe adding some points here, so gathering some data that is maybe corresponding to this part, you can maybe decrease here the confidence intervals and maybe also get a better or sharper shape here. So as you can see, the sampled functions are also varying much more. The question is now, so we had this maximum likelihood estimation, we had the maximum a posteriori estimation, which already did a good job. But what is maybe now the advantage for the robotics application? So first of all, in robotics, we are always interested in the uncertainty of our estimates, because this gives us an indication about how well we are doing with our predictions. So uncertainty is, of course, a good thing. So, and we get also the variances. So as you saw, when we increase the degree, we get larger variances in the end, and therefore larger confidence intervals, and therefore we can get there something. And as I said, we can also determine the regions on uncertainty in our estimates. So what we saw on the left side, so we have there very uncertain areas. And what we also can do, which is a side effect, that the prior is basically of the same functional shape and form as the posterior, is that we can then take the posterior again and put it just in as prior for our additional learning. And this is one thing that we cannot do when we have a point estimate in the end. So the incremental learning is really a thing that is an advantage in the end. So because you can just take new data, do the fitting again, or just use the equations again, and then you can get an updated posterior in the end. And with this you can do then the incremental learning, and this is really a big advantage. We are now talked a lot about the linear regression, and we talked about it in a specific way. And here we used basically the view that we want to have a discriminative model. So we could write so that's what we're interested in P of y given x, but via Bayes rule we can of course also rewrite it like this, so that we have here the relationship P of x given y times P of y divided by P of x. And of course the marginal likelihood we can describe again by using the integral over this. And we are now, from our definition in the beginning, we decided just to model this. So this was just the normal distribution over y given the mean, which was the linear function, and the sigma square. But when you think about it, you could also just get the same by modeling P of x given y and P of y, and or just the joint distribution of P of x and y. And this is then the distinction here. We have discriminative models where we directly model this conditional probability, or we can just use a generative model where we model basically these parts here. And what should you do now in the end? Use either a discriminative or a generative model, and there's no definitive answer. For certain tasks it might make sense to model directly the data, so because this is what you would basically do when you have a generative model. In other parts it's maybe easier to just use the discriminative model. So discriminative models are for inference definitely easier, because you don't have to do the integral and the other parts. So because you get directly out what you want, especially when you have very high dimensional data, like images or something like this. It's maybe not so easy to find a generative model which is fitting to the data very well. And therefore, this leads maybe also to complexer models in the end for the generative part. The other part, which is an advantage maybe of the generative model, is when you're directly modeling P of x given y, you basically have a data generation model, because you can now sample just new data that fits to your labels. And then you have therefore it's called generative model. And what is also an advantage of the generative model is that you can fill in missing data, because you have the generation process. and therefore you can then estimate missing parts using your model that you learned there. And one advantage also of the generative models is basically that you can easily integrate expert knowledge by modeling the generative process in a certain way. But yeah, as you saw with the discriminative model, we have also the ability to have a prior in the end. And with this, we can also integrate somehow maybe knowledge about where the parameters should lie or something like this. So with this distinction between the generative and discriminative model, to which we also come then in the next lecture a little bit more, because for the classification task, which we cover in the next lecture, we can have actually generative models and can show there something with this. So, but to give a short summary, as you can see here, these pictures basically show basically the progression that we made. We started with linear regression, so for linear functions in the beginning, then went over to the nonlinear functions by using the nonlinear transformation. And we saw that the maximum likelihood estimation can lead to a severe overfitting, and by using then the map estimates, we are then getting a better job here. And then we ended with the Bayesian linear regression, where we also get the full posterior over the parameters in the end, and with this we can then also have the confidence intervals. And in the end, we also looked a little bit on the discriminative and generative models, but as I said already, this will be also covered in a little bit more detail in the next lecture. And with this short summary, I'm coming to an end. Thank you for your attention, and see you next week.